Welcome to G Fun Facts Online. Today we are stripping away the noise of the modern world to focus on a singular, silent moment frozen in stone for 80 million years. We are traveling to the Adriatic coast of Italy, specifically to the limestone cliffs of Monte Cònero. This is a story that begins with a group of rock climbers and ends with a terrified stampede of ancient marine reptiles. It is a narrative that combines the slow, deep time of geology with the frantic, heart-pounding seconds of a biological disaster. On a spring morning in 2019, amidst the salt spray and sunlight, climbers were scaling a vertical face known as the lavella slab. They were searching for friction in handholds. What they found instead were thousands of chaotic grooves and crescent-shaped depressions etched into the white stone. To an untrained eye, these might have looked like weird erosion patterns or the borings of ancient clams. But to the geologists who later examined them, these marks told a violent story. They were not random. They were the frantic, thrashing footprints of a mass exodus, a stampede of Cretaceous sea turtles fleeing a cataclysmic earthquake that shook the floor of the ancient Tethys Ocean. To truly understand the gravity of this discovery, we have to first understand the stage upon which it happened. Monte Cònero is a geological anomaly. It rises abruptly from the coastline south of Ancona, the only major limestone relief for hundreds of miles. The rock that forms these cliffs is known as the Scaglia Rossa. In the world of geology, the Scaglia Rossa is legendary. This is the same formation that, in the nearby town of Gubbio, provided the first chemical evidence of the asteroid impact that killed the dinosaurs. It is a pelagic limestone, which means it was formed from the slow, incessant rain of microscopic plankton shells drifting down to the dark, quiet bottom of a deep ocean basin. 80 million years ago, during the Campanian stage of the late Cretaceous, the rock face the climbers were scaling was soft, white mud lying hundreds of meters below the surface of the Tethys Ocean. This ocean was a vast, tropical seaway, separating the supercontinents of Laurasia and Gondwana. The area that would become Italy was then a submerged promontory called the Adria microplate. It was a realm of silence, far from the crashing waves of the shore, where sediment accumulated at a rate of mere millimeters per millennium. It was supposed to be an environment of absolute stillness. But the discovery at the Lavella outcrop shattered that image of tranquility. The slab, now tilted nearly vertical by millions of years of tectonic pressure, revealed a surface that had been churned and scratched on a massive scale. These were trace fossils, records of biological activity rather than biological remains, covering hundreds of square meters. These were not the wandering trails of a lonely scavenger. They were the chaotic, overlapping marks of a crowd. Reconstructing this event requires a blend of forensic geology and biological imagination. Based on the study led by geologist Alessandro Montanari, we can piece together the timeline of the Cretaceous Stampede with chilling precision. Picture a day like any other in the late Campanian. The water is warm and rich in nutrients. A massive aggregation of sea turtles is loitering near the seabed. Why they are there is a matter of debate. Perhaps they are resting on the soft mud, a behavior seen in modern loggerhead turtles, or perhaps they are feeding on a bloom of jellyfish or bottom-dwelling crustaceans. Suddenly, the silence is broken. A deep, low-frequency rumble vibrates through the water column. The seabed shudders. It is a high-magnitude earthquake, a common occurrence in the tectonically active Tethys region, where the African and Eurasian plates are grinding against each other. For a sea turtle, water is an excellent conductor of sound and pressure. The shockwave would have hit them like a physical blow. Instinct took over immediately. In a unified spasm of panic, the herd bolted. The tracks on the Lavella slab show the mechanics of this flight perfectly. The marks are deep, rhythmic scratches made by the tips of long, powerful flippers. These are swimming tracks, not the footprints of an animal walking on land, but the scars left by animals swimming just centimeters above the bottom, their flippers digging into the mud to generate maximum thrust. The chaotic orientation of the tracks suggests total confusion, a scrambling mass of bodies colliding and turning, desperate to escape the shuddering seafloor. But the earthquake did more than just scare the turtles. It destabilized the underwater slopes above them. Moments after the stampede began, a massive volume of sediment collapsed, triggering a turbidite, which is essentially an underwater avalanche. This avalanche is the key to the preservation of the tracks. Normally, footprints in soft ocean mud are transient things, washed away by currents or erased by burrowing worms within days. But the turbidite acted as a sealant. A thick slurry of mud and sand roared down the slope, burying the freshly made tracks under meters of sediment in an instant. The disaster that terrified the turtles was the very agent that preserved their memory. The mud hardened into rock, the epochs passed, the Adria microplate was squeezed and lifted, and the ocean floor became a mountain. Finally, erosion revealed the snapshot of that terrible afternoon. But who were these turtles? No shells were found on the Lavella slab, only the scratches of flippers. However, the size and shape of the tracks allow scientists to narrow down the suspects. The tracks suggest animals with a carapace length of 1 to 2 meters, or 3 to 6 feet. This rules out smaller coastal turtles. We are dealing with true pelagic giants. In the late Cretaceous, the European seas were home to titans. While the famous Archelon patrolled North America, Europe had giants like the recently discovered Leviathanoculus enigmatica. The Monte Cònero turtles were likely smaller than a full-grown Archelon, but they were substantial animals, likely early members of the Chelonoidea, the superfamily that includes all modern sea turtles, or perhaps members of the Protostegidae, an extinct lineage of giant, leathery-shelled turtles. The shape of the tracks matches the biomechanics of the power stroke used by modern sea turtles. Unlike plesiosaurs, which used 4 flippers in a complex underwater flight, or mosasaurs, which used their powerful tails, sea turtles rely almost entirely on their front flippers for thrust. The tracks at La Vela show exactly this: deep, parallel gouges from the front limbs, with little to no trace of the hind limbs. The sheer number of tracks is the most telling clue. Mosasaurs and plesiosaurs were generally solitary hunters. Sea turtles, however, are social animals during specific phases of their lives. Only turtles would be found in such a density, all reacting to the same stimulus at the same time. Interestingly, the La Vela discovery is not the only reptilian secret Monte Cònero holds. Distinguishing between them is crucial. Years prior, in an older rock formation called the Maiolica, geologists found a trackway named Coneroichnis marinus. This consisted of distinct imprints suggesting a large marine reptile punting along the seafloor, likely a pliosaur. The contrast is stark. The pliosaur tracks represent a solitary hunter patrolling a Jurassic seabed, while the La Vela tracks represent a mass social event in the Cretaceous. Together, they make this mountain a Rosetta Stone for marine reptile behavior. Trace fossils in deep-sea environments are vanishingly rare. To find tracks made at depth requires a miraculous alignment of conditions where the animals interact with the bottom and the sediment is preserved immediately. This leads us to the ethology, or behavioral study of the deep. Why were so many turtles on the seafloor? Modern sea turtles spend most of their lives in the open ocean, but dive to great depths to forage or rest. Loggerhead turtles have been recorded sleeping on the seabed to avoid predators and conserve oxygen. The resting hypothesis is a strong contender for the La Vela site. Imagine a dormitory of hundreds of sea turtles scattered across the soft mud, resting between bouts of feeding. The stampede behavior also highlights the sensory capabilities of these ancient animals. Modern turtles are highly sensitive to vibration. An earthquake generates P waves and S waves. In water, the acoustic shock of a P wave can be deafening. The fact that the entire herd reacted before the sediment avalanche buried them suggests a highly attuned sensitivity to their environment. They didn't wait to see the mudslide. They felt the earth move and ran. We must also consider the world they were fleeing into. The late Cretaceous Mediterranean was a tropical paradise, but a dangerous one. Surfacing for a breath, a survivor would have seen a sky patrolled by pterosaurs. The water itself was the domain of the mosasaurs. These were the dragons of the Cretaceous seas, growing up to 17 meters in length, with jaws adapted for crushing shells. A panicked herd of turtles would have been a ringing dinner bell for any mosasaur in the vicinity. Yet sea turtles were survivors. Their strategy relied on armor, speed, and swarming. The discovery acts as a bridge between deep time and live time. Usually, geology records processes that take millions of years, but phenomena known as event stratigraphy capture a single moment. At La Vela, we are looking at 5 minutes of the Cretaceous. We can see the direction they turned. We can see the width of their strokes. We can almost hear the muffled boom of the quake. This discovery also offers a poignant mirror to the present. The descendants of these ancient refugees still swim in the Adriatic waters today, but they face a different kind of stampede. The earthquakes they flee now are the thrum of ship engines, bottom trawling, and seismic air guns. The Scaglia Rossa tracks remind us of the resilience of this lineage. They survived the asteroid, the cooling of the Eocene, and the ice ages. Finally, we must appreciate the science of interpretation. Validating the stampede hypothesis was rigorous. The team had to rule out abiotic causes, like fluid dynamics or tool marks. They analyzed the regularity and symmetry of the tracks, finding the complex bilateral symmetry of a swimming animal and the specific entry and exit angles of flippers. They ruled out other animals. Fish fins don't leave deep gouges, and crustaceans leave multi-legged patterns. Only marine reptiles with paddles fit the profile, and the directionality of the tracks combined with the turbidite layer confirmed the mass movement event. The Cretaceous Stampede of Monte Cònero is a narrative masterpiece of the fossil record. It gives us a plot, characters, and a setting preserved in pink stone. As we look at those frantic scratches, we witness a moment of primal instinct from 80 million years ago, a testament to the will to survive, etched in stone. The cliffs stand silent now, watching over the Adriatic, but for us, the tracks allow us to reach back through the eons and feel, for just a moment, the pulse of the Cretaceous ocean. Thank you for listening to G Fun Facts Online.